Good day, ladies and gentlemen. It's Vernon here. We're here today to talk about lesson 3.5, day 3. Hopefully, Wednesday's lesson went well and you were able to get a whole bunch of work done on those two worksheets you worked on yesterday in class. That would be Thursday. So today what we're going to be talking about is I'm going to do a quick little lesson on equation modeling. I'm also going to go through another example with you. And then you'll be having some more time to work when you're done. So lesson 3.5 also includes equation modeling. So not only are we solving equations, but we're also going to be talking about where are some situations where logarithms show up in our world. There actually are a lot of different scenarios where they show up. We have talked about some of them in the past, but some other areas would be like orders of magnitude, magnitudes of earthquakes. So how strong was the earthquake? Chemical acidity, you would have seen that in your science classes. Those are oftentimes base 10. And then Newton's law of cooling is another one that exists. Again, we're not going to talk about all of these different models. We're just going to focus on Newton's law of cooling today. The book does talk about all of them. If you're interested in a different area, definitely do that. But let's jump in and talk about Newton's law of cooling. Basically, Newton's law of cooling says that if I were to take a cup of hot chocolate outside on a cold day, that cup of hot chocolate isn't going to stay hot all day. Eventually, it's going to slowly cool until it becomes the temperature of the outside temperature, or the temperature of the medium in the room. Now, this very complex equation that is listed here is going to be the equation that helps us understand what's happening. I'm going to try to annotate that equation a little bit for you. So T of T would be the temperature at time 0, or at any given time. So the temperature, there we go. So that's the temperature at any given time. That's just function notation. We have some other variables in this equation. We have T sub m, T sub 0, and then we have a K and a T. Remember that E is that natural base E, so we don't actually have to solve for that variable. That is a number in our calculator already. T sub m is the temperature of the surrounding medium. So that's given to you guys right here. And what that means would be, that would be like the temperature outside, for example. Now, the T sub 0 is the temperature of the object. So in my example, that would be the temp of the hot chocolate. Now, as you're thinking about this, you're probably like, oh yeah, I can visualize some varying situations where this would occur. K up here, this one is going to be known as your constant of variation. We've talked about constants of variation, and basically this constant changes depending on what we're doing. So oftentimes we're going to find that we're going to solve for the K value, plug it back in, and then solve for a different variable. T is time. So that is how long has the object been cooling in the surrounding area. Let's take a look at an example together so we can work through this. It says a hard-boiled egg at temperature 96 degrees Celsius is placed in 16 degrees Celsius water to cool. 4 minutes later, the temperature of the egg is 45 degrees Celsius. Use Newton's law of cooling to determine when the egg will be 20 degrees Celsius. So here is our equation from the previous slide. I did copy that over. What we're actually trying to find is how long it takes for our egg to cool to 20 degrees Celsius. They do give us some information. They give us 96 degrees Celsius and 16 degrees Celsius water to cool. They also give us a secondary piece of information that 4 minutes later, the temperature of the egg is 45 degrees Celsius. So as I start to think about all these different variables in my equation, I recognize that I'm going to need to identify what is T sub 0, what is T sub m, and then do I know any other values as well? Well, in this particular situation, T sub 0 is known as the temperature of the object, or in this case, 96 degrees. That's going to be the temperature of our egg. T sub m is going to be the temperature of the area that it's surrounding, so that's going to be our temperature of our water. So in this case, that's going to be our 16 degrees. We don't know K, but we do know that when T equals 4, the temperature equaled 45 degrees. So in order for us to find out when the egg reached 20 degrees, we're going to have to first figure out what is our K value. So that's our first step, find K. This K value is going to be consistent in all of the equations that relate to this particular problem. So plugging in the information, we know that the temperature at time 4 minutes is going to be 45 degrees. T sub m is 16 plus T sub 0, 96 minus 16, and then we have e to the negative k times 4. All right, so at this point, this looks a lot like the equations we've been trying to solve. So I would begin by subtracting my 16 from both sides. When I do that, I get 29 equals, and at the same time, I'm going to simplify this down to my 80 e to the negative, and I'm going to go ahead and say that's a 4k up there. Then I'm going to divide both sides by 80. Now, I could get the decimal approximation here, but that's not necessary because eventually I know I'm going to have to do some logarithm stuff, and that's probably not going to be helpful to have a big decimal there. So at this point, I'm going to go ahead and scroll down on my page, give me a little more room, and I need to figure out how do I get rid of that e. Well, in class earlier this week, I taught you that if you take the natural log of base e, they cancel each other out. And it leaves you with an answer of the natural log of 29 over 80 equals negative 4k. To finish solving for k, we would divide both sides by the negative 4. And now I can type this into my calculator all at once. Natural log of 29 divided by 80. I can go ahead and grab my calculator here. Slide it over. Oops. There we go. Turning it on, we can go natural log of 29 divided by 80. Notice that I'm closing that parenthesis, hitting enter, and then I'm going to do the dividing by my negative 4. When I do that math, I get 0.2536, so I'm going to go ahead and do that 0.2537 by rounding. 0.2537. So that's our K value. Now I have enough information, I can go back and use that 20 degrees Celsius and solve it for T. So I'm going to go back up to my problem, and in a step 2 of it, I'm going to find T when the temperature is equal to 20 degrees. So plugging in what I know. I know that I want the temperature to be 20 degrees. I know T sub m is still going to be 16. I know that T sub 0 is still 96. And now I don't know T, but I do know that K is negative 0.2537. I do encourage you to keep that decimal as long as you can, at least 4 decimal places, just for accuracy of the problem. Again, we're going to follow a very similar process that we did on the previous side. So subtracting 16 from both sides gives me 4 equals, we know that 96 minus 16 is 80, e to the negative 0.2537 t. Again, we want to get rid of that 80 before we do anything with the e. So 4 over 80 equals e to the negative 0.2537 t. And now we can take the natural log of both sides. Taking the natural log of both sides gives me the natural log of 4 over 80 equaling negative 0.2537 t, and dividing by the negative 0.2537. Go ahead and grab your calculators this time on your own. If you need to, pause the video and find out how long does it take for our egg to reach 20 degrees. Hopefully when you entered that into your calculator, you would have gotten 11.808 minutes. Any questions on that problem? Please make sure you note them, and we'll go ahead and talk about those on Monday when I return. If you needed to, you could have paused and rewinded the video. That sometimes is helpful for those people who are struggling. Let's go ahead and look at one other example. I'd like to look at an example where it's a little bit more complex and kind of walking through all those different areas. So as I look at this problem, I see that we have logs on both sides, but I see that we're adding these two logs together. That's a pretty complex problem. So I know that my properties say that I can actually take log of x minus 2 times log of x plus 5 if I want to condense it into a single logarithm. On the other side, I know that that 2 can jump up as an exponent, giving me log of 3 squared. As I look at both sides, because these both have a log on both sides, those will cancel out. It's kind of like dropping the base. We can also drop that logarithm. It's one of our early properties in this chapter. At this point, I'm going to expand this because it's two binomials multiplied together. So if I FOIL it out, I'd get x squared minus 2x plus 5x minus 10 equals 9. And then combining like terms, x squared plus 3x, I'm going to also subtract that 9 over at this point, minus 19 equals 0. There are no pairs that will add to 3 and multiply to negative 19. So at this point in the problem, I'm going to use the quadratic formula. So I'm going to kind of go off on the side here and do the quadratic formula because remember I'm trying to solve for x. Using the quadratic formula here, I get x equals negative b plus or minus the square root of b squared minus 4 times 1 times negative 19, all divided by 2 times 1. I can simplify this down to negative 3 plus or minus the square root of 85 over 2. And I'm not able to simplify this. But for the sake of this problem, I am going to approximate my x values. The reason why I'm doing this is because I remember that logarithms, I cannot take the log of a negative number. So it's kind of like an extraneous solution that shows up. When I do this approximation, I get 3.11. And that x is approximately negative 6.11. Well, looking back at my original problem, if I were to plug in 3.11, that would be okay. 3.11 here would be okay. But negative 6.11 would cause this to be a negative number. It also would actually cause this to be a negative number. So when I write my solution, I'm going to be sure not to include this because that is an extraneous solution. Remember, it works out algebraically, but it's not actually a good solution. The only answer I'm going to write for this one is x equals 3.11. I hope that cleared up some of your questions. For tonight's homework, you're going to be doing this assignment here. I also want you guys to go ahead and do a couple more problems that I have in this lesson just to show me it's my check-in for you while I'm out. So I know where we need to work more. And remember, if you have any questions, be sure to mark those questions so that we can take care of them when I return. Hopefully you're having a great day.